In the Bronsted-Lowry category of acids and bases, which is considered the second most diverse category, acids are considered the proton donors and bases are considered the proton acceptors.
Okay. In this equation, HCl is the acid. It's a strong acid. And it is the acid because it donates its hydrogen or H plus ion to water. And that makes hydronium. So you can see that it has 3 H pluses now instead of 2. Now this makes water the base because it's the proton or the hydrogen plus ion acceptor. And like I said, it has 3 hydrogens now instead of 2. And this is the conjugate base, and this is the conjugate acid. As you can see that it's lost its hydrogen, and this one has gained 1. So you have base, conjugate base, conjugate acid. Done. Okay, so in this is an AP question off the 2010 AP test. It's online, and it tells us that methylamine, this molecule, is added to a solution of hydrochloric acid. Now, and then it asks us to find the balanced net ionic equation for this reaction. Okay, so on the reactant side, we have methylamine, CH3NH2, that reacts with hydrochloric acid. Hydrochloric acid. Okay, and that's aqueous. It's a strong acid. Strong acid. And this is a base because it has it's an amine. Amines are always base, which amine is derived from ammonia. And that's also aqueous. Okay, and that reacts to form. Now this is the predicting products part. And so we have to know that this is Bronsted-Lowry acid-base reaction. Now the acid, HCl, is going to donate an H plus ion, so here, to the base. So what we're going to get is CH3NH3, since it's getting a new hydrogen ion. So, yes, plus, because the hydrogen is a positive ion, so it's going to make this a positively charged molecule. So then plus Cl negative, which is left over when the H is lost from the HCl. Alright, so now they wanted us a net ionic equation. So this is a molecule that doesn't dissociate further. It's going to stay like this. It's not ionic. Now that plus H plus Cl negative, those two. This is a weak acid because it's the conjugate acid of this base. Now this is weak. So it's not going to dissociate further either. CH3 and H3 plus Cl negative. Now you can see how the H goes to this base. These cancel out because they're spectator ions, and you're left with CH3 and H2 aqueous plus H plus aqueous goes to CH3 and H plus aqueous, right? Aqueous. Oh, and H3. My bad.
Conjugate acids are created after the proton is transferred to the base, and conjugate bases are what's left of the original acid after the proton was lost and given to the base. Strong acids form weak conjugate bases which are weaker than water, which means that they're really, really weak. An example of this is hydrochloric acid and the chlorine atom. Weak acids also form weak conjugate bases, but they're stronger than water, even though they're still considered weak. Both strong and weak bases form weak conjugate acids, although the strong bases form the weaker than water conjugate acids, and the weak bases form conjugate acids that are stronger than water but still weak. Water is amphoteric, which means that it can act as either an acid or a base in a reaction, which is just another way that water is special. At 25 degrees Celsius, the equilibrium constant of water is 1 times 10 to the negative 14th, but it's only at that temperature because the equilibrium constant changes as the temperature changes. The equilibrium constant of water is also considered the concentration of the hydronium ions multiplied by the concentration of the hydroxide ions, or Ka times Kb.
Go.
The water in this bowl is self-ionizing. The molecules of water contained within this bowl are ionizing each other, forming hydronium and hydroxide ions. As we speak, this process is occurring, and will occur for any container of water. Trust us, it's happening right now.
For the general reaction between a Bronsted-Lowry acid and water, that is, Bronsted-Lowry acid plus water equals hydronium plus the conjugate base of the Bronsted-Lowry acid, based on the normal way that an equilibrium constant would be determined, the equilibrium constant will be the concentration of hydronium at the end times the concentration of the conjugate base at the end divided by the concentration of the acid at the end. For this acid's conjugate base, when it reacts with water as a Bronsted-Lowry base, the equation will be the conjugate base plus water will produce the original acid plus hydronium. And again, we can calculate the Kb for this reaction the normal way that you calculate equilibrium. If you multiply these two expressions, that is, if you find the Ka of the acid times the Kb of its conjugate base, you'll find that all of the terms will cancel except for hydronium times hydroxide, which we know equals a constant in a solution at a given temperature. So at 25 degrees Celsius, this will always equal 10 to the negative 14th. This means, as we've talked about before, that for a stronger acid, the conjugate base will be weaker, and for a stronger base, the conjugate acid will be weaker. This also makes conceptual sense, because an acid that very easily gives up its hydrogen ion to water will not easily then take a hydrogen ion from water when it as its conjugate base.
So all this that we've been telling you about conjugate acids and conjugate bases has some interesting implications. For example, take the ionic compound NaF. You'd think, with just sodium fluoride, it's just a random salt. It shouldn't have any special attributes in terms of acidity or being basic. You'd think it's just a regular ionic compound. But you'd be wrong. Would you believe that this is basic? Let me show you why. So, NaF has a sodium ion. Sodium salts dissociate completely, if you remember the song. So, you left with Na plus ions and F minus ions. Yes? Now, you'll notice that Na plus is the conjugate acid of a base, specifically NaOH, which dissociates normally into Na plus and OH minus. So you'd think, oh, that's interesting, the reverse reaction can occur, that would reduce OH concentration and would make the solution more acidic. You'd be wrong, because this is a strong acid, meaning, sorry, a strong base, but this is a strong base, meaning the reverse reaction never occurs. Which makes sense, because, you know, sodium always dissociates. So this doesn't happen. So this just stays in solution, sitting around. It's the fluoride ion that really matters here. Recall the reaction HF goes to H plus F minus. Now, this reaction, this is a weak acid, meaning this reaction is reversible, meaning when we increase the F plus concentration, we are actually making this reaction occur. Where this is an actual molecule. Now, what happens then, we're increasing F minus concentration, meaning the direction of the reaction, the position of equilibrium, should shift towards HF. What this does is decreases the H plus concentration. Therefore, if we take the general reaction for the self-ionization of water, we know that H plus is decreasing. This means that this is a liquid, meaning the product of these two must be the same. OH minus concentration increases, meaning the solution becomes more basic. Therefore, NaF is a base.
The Lewis category of acids and bases, which is also the most diverse category, considers acids to be electron pair acceptors and bases to be electron pair donors. This is the opposite way of what we think of for the Bronsted-Lowry. It is helpful to know the Lewis dot structures so you can determine which atom the electron pair is coming from in order to determine which one is the acid and which one is the base.
Okay, so you may recognize this reaction from earlier. It was one of our Bronsted-Lowry reactions. Well, as a Bronsted-Lowry reaction, it is also a Lewis reaction. Now, it's a Lewis reaction because in a Lewis reaction, the acid is the electron pair receptor, and the base is the electron pair donor. So here's our base as per the Bronsted-Lowry reaction. Now, this is also a base in the Lewis reaction because it donates an electron pair. This pair of electrons is going to be provided to this H. So this H is going to bond with this pair of electrons. Now, the H isn't donating any electrons, it's just accepting these ones, which is why this is an acid, and this is a base. Now, Lewis reactions only work with coordinate covalent bonds, which are bonds where one molecule provides the electron pair and the other one accepts it. The other one doesn't provide any electrons. So, like I said, this is accepting this pair that is provided only by the H2O, base acid, and then it goes just like a Bronsted-Lowry and makes conjugate bases conjugate bases and conjugate acids. Okay, whatever.